Hi guys, welcome to my channel, The Analyst. Today we'll have a look at linear regression. Alright, it's a supervised machine learning algorithm. So let's just directly jump onto the demo. For the purpose of this video, I'll be using the crime dataset. As you can see over here, there are many features, right? And only so there are 16 variables and 47 observations. Okay. In such cases, mostly what happens is that the data could, the model could overfit. We'll see how to get rid of the overfitting in our next video. Alright, but for now, for the purpose of this video, let's continue. The first thing that I do is that basically I clear my environment, uh, set the seed, and I read the data. Alright, crime data. Here exactly I show you the first 6 records. Right. Then now what I do is that I use the LM function basically to perform a linear regression. Okay, my crime, which basically is my last column, is basically my response that I want. Okay, and with crime as the response, basically it's a function of all the other attributes that I have. So let's see, after performing linear regression on the data, okay, then I plot the model. On the plot, what you can see over here is that it's kind of like uh, distributed evenly across the zero line. Okay, not perfect, but yeah, it's good enough. uh, this is basically seen in the residual versus fitted. Okay, residual is basically the difference that you get between what you originally observe and what is predicted. Okay, so these are all the residual errors, pretty much evenly distributed across the zero horizontal line. Then we have the QQ plot. QQ plot basically shows you exactly whether the data is normally distributed. Even over here, uh, between one standard deviation, you can see that pretty much all the data is concentrated. Okay, it's not perfectly a normal distribution, but it will do. Okay. Then from the third plot, basically it's just a scaled version of the first plot. Uh, so you have the standardized residuals, okay, which basically is more sensitive to the data. So over here again, pretty much I don't see a problem over here. Most of the x values look to be independent of each other. Then basically what you have is this, right? The next plot, which is residuals versus leverage. Now over here what you can see is that basically the ones that are further away from zero line, right, they are like high influential kind of points. Okay, and Cook's distance basically tells you that, if it lies anywhere beyond this, they could be detrimental to your model if it's an outlier. Okay, so you need to know the purpose of how exactly, what exactly that point denotes. But over here in this example, we don't have anything as such. uh, if we leave these outliers, then what happens is that the model tries to fit everything in. Okay, so it destroys the pattern that it's trying to form. Alright, so moving on, pretty much we can say that we can use a linear regression model, right, based on the fact that you have your data points that are evenly on both sides, kind of like a normal distribution, and so okay. Now what I do is that basically I take a summary of the model that we had over here, And from the summary, what I can see is that I'll come to know for each of these attributes which are important and which are not. Okay, the ones that are important, they basically will have lower significant codes. Okay, their p values will be much lower. Okay, so as you can see over here, these are pretty important. Okay, and these values over here, p02, lf, mf, these all basically have really high p values, so they have less significance. So we don't necessarily need to keep them while forming a model. Alright, so let's remove them out and keep only the significant values like this. So here I'm considering every value wherein probably you have your p value which is greater than or lesser than or equal to 0.05. Okay. Another thing to notice over here, you get what your error is, and you have your r square, adjusted r square. Higher r square better, lower errors better. Okay. But to see how exactly these points influence the model, we just remove them off, okay, and consider only the ones wherein the p values are below 0.05 and check the effect that it has basically on the error and the adjusted r square. Okay, that's what I did over here. I considered only those attributes that basically have a p value of lesser than or equal to 0.5, 0.05, and then I made the plot. Alright, similar to what we did in the previous steps. Again, data is not really normally distributed, but for the sake of this video, let's continue. Right. I take a summary of the new model. So basically model 2 is wherein I only consider those attributes that have some kind of significance. And if you see over here, you have a lesser error, not that good because the previous one was like 209.1, but it's improved marginally. Okay, and even you have a better adjusted r square. Now basically that we already have our model, so what we can do is that given that you want to predict what a crime is for particular values of the attributes, you can just plug them in. Okay, I form a data frame and basically I feed that to the model and I get a value, alright, of exactly what's the crime, 1304.251. Let's so this is exactly your linear equation that you have. Okay, so the model basically has come up with an equation, you feed the values to the model and you can get the predicted value, right? Let's basically see evaluate how good our model is, okay, by calculating the r square value. We will make use of cross validation in this case. Like I explained in one of my previous videos, in cross validation, we do not just divide the data into a train and a test set, because when you form the test set, you never know whether the samples that you've considered in it, okay, represents like the entire data set, the entire population, right? So what we'll do is that we will make 5 folds over here. Okay, so we'll divide the data into 5 parts. We will use 4 parts to basically train, and then we'll validate it on the 5th part. Now this validation part will keep on changing. Okay, so we'll have 5 validation parts, and the remaining of the data will be used to train, right? And then we'll aggregate basically all the errors and check how good our model is. So that's what we did. We do cross validation over here, and then we have to find the r square value. Now, to calculate the r square value, basically we have a formula which is 1 minus sum of squared errors divided by the sum of square totals. Okay, to find sum of squared errors, you basically have a formula in place, and for sum of square totals, you have the way. Okay, as seen, the cross-validated r square value is basically 0.63. Okay, this is not really a good value, but then again, like I said earlier, we have probably what's happening is that uh, our model is overfitting the data. Okay, this normally happens due to less records for one. Like you can see, you have like 47 observations only, and a lot of attributes present. Okay, we will see in the next video. We'll use principal component analysis basically to see how we can reduce this overfitting. Okay. Other than the LM model that I just showed you, the LM function, you can also use the generalized LM function. Okay, that's basically GLM. Yeah, the only difference in it is that there is a family attribute that is present in it. Now, why family attribute is because when we were evaluating using the LM function, it is assumed that the error distribution, where is that? Alright, when you're using the LM function, we are assuming that the error distribution is normal. However, that is not the case. Okay, always. So then we can use the generalized LM function to basically have a distribution, your error distribution that basically fits correctly. Alright. I've just used Poisson over here. Poisson. In this case, you could basically select the family that. So if you just type in GLM over here, you can read a bit more about it. This is out of the scope of this video at least. Okay, you can read about families over here. Okay, so if you scroll a little bit down, you can see what all families are there. Okay, by default you have the Gaussian family. This will function same like the LM. Okay, Gaussian family basically you have your normal distribution. All right. In terms of, say for example, your crime data. Okay, your crime column has 0 and 1 values. Then you'll probably have to have some kind of a logarithmic function to fit the data. Okay, in that case you can use the binomial family and so on. Logit family basically to fit the data. All right, you can use binomial in that case. Yeah, I mean that's it for this video. Okay, one other important point is that when you're using GLM, like in the previous function, we used the r square value basically to compare models, where the higher r square value probably meant that the model is better. Here we have something called as AIC. Right. The lower the AIC, the better. So if you have multiple models with different AICs, the model with the lowest AIC is the best. Right. Okay guys, that's it for this video. Thank you very much.